Bismillah Rahman Rahim and Assalamu alaikum. This is Faryaz Javed, roll number 21 T07 from Telecommunication Engineering Department UT Texila. So today I'm going to solve lab manual 6 of digital signal processing, that is DFT properties and FFT. Moving toward lab objective of this lab, that is basically a representation of discrete time digital signal interfrequency domain via FFT, the resolution of spectrum, the computation of magnitude, phase and power spectrum, and then the spectrum leaking. So basically, a decimation frequency involves the reducing the number of frequency samples that is basically achieved by the downsampling in frequency domain. On the other hand, the decimation in frequency it involves the reducing the number of time domain samples that is usually done by the downsampling filtering in the time domain. So the main difference between both of them is the we use frequency for decimation frequency and time for decimation in time, and then these both techniques are used to reduce the signal complexity while preserving important information. So moving to our task one of today's lab, that is write a MATLAB program to validate the above given decimation. Program first divide the given signal into even and odd sample, then calculate the DFT for even odd samples separately, and then merge both of them. Where G of k is the DFT of even part and H of k is the DFT of odd part. So the output to this task is as shown. So in this code, we basically use a two type of yes, here is the output. So in this code, we basically define a MATLAB function named validate decimation, which basically takes two inputs, the signal and the decimation factor. And then we'll have the even and odd sample calculations. It calculates the number of even and odd samples in the signal and then divide the input signals into two parts, that is even samples and odd samples. Then we'll have the DFT calculation, which compute the discrete Fourier transform of both even and odd sample separately using FFT function, and then we'll merge them using a DFT. Here is the formula to which we can merge them and calculate the DFT, that is x is equals to g plus exponential minus I 2 pi k divided by n into a decimation factor. So in the plot we will have the original signal and then the reconstructed signal after decimation for the visualization. So the reconstructed signal after decimation is plotted in the second subplot, and here is the output. Moving toward task 2 of today's lab, that is check the above program for a signals given below x1, x2, x3, x4, 5, 6, 7, and 8. Observe and find any symmetry in frequency representation. Also match the calculated DFT with standard function of MATLAB, that is FFT function. So in this code we basically check the signals function. This function iterates through each of the given signal, validates the decimation process, and compares the calculated DFT with the standard function FFT function. And then we'll have this validate decimation function here. This function validates the decimation process for a given signal and decimation factor. It plots the magnitude and the phase of the calculated DFT. So by running this script, we can observe that the magnitude and phase of the calculated DFT for each signal and also compare with DFT obtained from the standard MATLAB FFT. Moving towards task 3, that is check the program in task 1 for a signal given below and compare it with a standard function x and y. So the output to a task 3 is in the command window. So, as we know that in task 1, we basically perform a decimation process. We divide a signal into even or odd sample and then calculate the DFT for each set and then merge them using a formula. In the task 2, this approach is slightly different. Here we directly compare the result of decimation process implemented in the task 1 with the result obtained using MATLAB standard FFT function. So the task 2 basically compare the result of decimation process implemented in the task 1 with the result obtained using MATLAB standard FFT function. The output include the original signal and a reconstructed signal after decimation obtained using task one's method. Here is the reconstructed signals output after decimation, and then the checking the signal y with the decimation of the original signal. So In general, the task 1 basically focuses on implementing and visualizing a specific decimation process, while the task 2 compares the result of this process with those obtained using MATLAB standard functionality to validate its correctness. Moving towards task 4, that is, we can further subdivide the above decimation up to two samples and calculate DFT of the two samples. The two samples DFT added to a four sample DFT, and the two four samples DFT form eight samples DFT, and so on. This 2 point decimation is called Radix 2 fast Fourier transform algorithm. Write a program myFFT that transform a given signal into its frequency representation using Radix 2 FFT algorithm. Pairs can be grouped via bit reversing. So, to implement the Radix 2 fast Fourier transform FFT algorithm in the MATLAB, we basically need the following steps. First, in the very first step, we perform a bit reversal to group a pair of samples. Then we'll perform recursive calculations for each level of FFT, combining pairs of DFT to form a large DFT, and then calculate the twiddle factor for each level of the DFT, and then combine the DFT of smaller sequence to obtain the final DFT below. Here is the MATLAB code. So the myFFT function recursively divide the input signal x into even or odd sample and then compute their FFTs separately. It then combines the FFT result using twiddle factor to reduce the final FFT result. The base case of recursive is when the length of input signal is 1, in which case function simply returns the input signal itself. So the last task of today is calculate the fast Fourier transform using your own function. Compare it with a standard function calculating DFT for the following signals. Now here is the output to our task 5. So in order to compare the fast Fourier transform using our own function task 2 with a standard function for calculating DFT for a given signal W, X, Y, and Z. So calculate the FFT using our own function for each signal, and then we'll calculate the DFT using MATLAB standard FFT function for each signal, compare the result. So we basically provide the FFT function with myFFT and then calculate using the myFFT function for each signal, and then calculate the discrete Fourier transform using MATLAB standard FFT function for each signal, compare the result, and result obtained is shown below. For both signal W, X, Y, and Z, will have the answer that is 1. So this is it for today's lab. Thank you. Allah Hafiz.